Gauss law is based on electric flux. So before we go to the Gauss law, we have to introduce what is electric flux. So I'm going to talk about electric flux first. Electric flux is basically the amount of electric field that passes through a surface. In simple case, when we have a uniform electric field like that, this is the electric field lines and with intensity E, and we have a surface that's perpendicular to the field. Like that, let's say this is a cross section of a surface. It is like this surface. For example, surface of this book, the electric field is this way, and that the surface is perpendicular to the electric field. In that case, we define if the surface area is A, electric field intensity is E, we call a flux of electric field by phi sub E, and we just define it as electric field intensity times the area, just intensity times area. That has a lot of other applications. Of course, in this case, is electric field, and sometimes we can apply to how much light passes through a window, for example. That's also flux of light through a window. Or how much, if you have a net inside water, you have flux of water through the net. How much water is passing through the net per unit time, or which is like the velocity of water times the area, if they're perpendicular to each other. Or you have flux of wind. There are lots of different ways you can measure flux. But here we're interested particularly in flux of electric field. And this is, in this case, we said the electric field is uniform and the surface is flat and the surface is perpendicular to the electric field. And then the unit of flux is the unit of electric field times unit of area, right? Newton per coulomb times meter squared, or Newton meter squared per coulomb. This is the unit. What if the surface is not perpendicular to electric field? The surface is flat, but it's not perpendicular to electric field. But E is still uniform. If E is uniform, let's say, again, we denote it by parallel lines, and the surface this time is like this. As I'm showing the cross section, of course, there's a dimension that way. So how much flux goes through this one? You see that if you make a perpendicular plane like that, and there's an angle here, theta, if this area is A, this area is A prime, the flux going through this area, A prime, is the same as the flux going through this area, right? Because all the electric field that goes through this area passes through the other area. Like this, right? And we know the flux through this one, which is phi equals to electric field intensity, which is uniform, times A prime. But A prime is smaller than A, right? By a factor of cosine theta, because this dimension is this dimension times cosine theta, so that we can say E times A times cosine of this angle theta. In this situation, we define an area vector, a vector for area, which is an unusual thing to do, but we do that in physics. When you have an area, we define a vector for that. The vector has to be uniquely defined. The vector is perpendicular to the surface, and it has a magnitude of the same as the area. Like in here, so if this is the area, this is a vector perpendicular to it. If we turn the surface, the vector goes with it, and for every orientation of this surface, this direction of this vector is uniquely defined. And if this is our surface, then this will be our vector, right? So I draw this vector like that. Let's say it goes like this. This is vector A. Area vector is defined as a vector perpendicular to surface and with magnitude A. For example, if this is like 0.1 square meter, we say this is 0.1 and it's in direction perpendicular to the surface, right? It is possible to define a vector like that. And in here, the electric field direction is this way, and the angle between the area vector and the electric field vector is also theta. If now you look at this, it should ring a bell. It has a meaning. What is E times A times cosine of theta? Does it ring a bell about vectors?
Dot product?
The dot product, yes. So in terms of this area vector, the phi can be simply written as E dot A, which is E times A times cosine theta. Remember that this is all for flat surface with area A and uniform electric field. Right? Now, what if the electric field is not uniform and the surface is not flat? Like if you have a non-uniform electric field, like that, and then you have a surface that's not flat. Let's say it's like this. This is like showing the cross-section of the surface. So it can be like the surface going through like this. How do we define the flux in that case? The electric field is smooth, and surface is also smooth. And that means that if you take a small enough region, that small enough region looks like a flat surface in a uniform electric field, right? So if you take a little piece of this, like dA, and it has a specific direction, and the electric field, let's say, in case it is in that direction, E, there's an angle between them. You can write the small electric flux passing through this piece, like dE, d phi E, equal to, according to this, because at small scale, the surface is flat and electric field is uniform, you can say it is E dot dA. And then we add all the small pieces of dE, because they're scalar, we just add all of them together. We get total flux. Total flux is equal to integral of the small piece E dot dA. This is the in general formula for flux. For closed surface, we take the area vector dA outward from the surface, because when you have a closed surface, there's an inside, there's outside, right? So we can always say that the dA is, by convention, is outward. And then the flux going out of the closed surface is equal to integral over the closed surface of E dot dA. And because it is a closed surface, we usually put a circle on the integral to show that it is an integral over the closed surface. Here, the integral is over the surface. Here, the integral is over the closed surface. If, in general, mostly the electric field is outward from the surface, we get a positive net flux. And that means that the flux is going out, generally. If the flux is mostly going in, you get negative contributions more than positive contributions possibly. This flux can be positive, can be negative. This is just a definition of flux in different cases. Now you know, for example, if you have a point charge at the center of a sphere, we can calculate how much flux going through the sphere. Let's say we have a sphere and we have a point charge Q inside at the center. And you know what kind of electric field the point charge creates around itself. So at any distance, particularly at distance r here, magnitude of electric field is kq over r squared, right? And it is also in the radial direction, and it's outward if the charge is positive, inward if the charge is negative. So if I put the r hat in here, it shows also the direction of it. Means the direction of r, right? And it works if q is positive or negative. If q is negative, means that it is inward. If it's positive, means that it is outward. And for any dA that we take over the surface of this sphere, the dA is also perpendicular to the surface, and it is outward. So dA, the magnitude is dA without vector on top of it, and the direction is also in the direction of the radial direction, right? This is, if this is r hat, this is also in the direction r hat, right? And now if you go back to this, we need to calculate this for flux going through this surface, right? What is the flux, total flux? Flux of the electric field due to this point charge is the electric field intensity at the surface times dA integrated over the surface. So integral over the surface, kq over r squared, r hat, dot dA, r hat, right? What is this dot product? What is r hat dot r hat? So dot product of a unit vector by itself is 1. R hat dot r hat is 1. So we get only the scalars here, right? So phi e becomes integral over the surface of the sphere, kq over r squared dA. I want to take everything that's constant outside. As we move around in here, q is constant. What about r? R is constant because we are on a sphere. Is it kq over r, all come out, r squared. And then we are left with integral of dA. What is integral of dA? It's total area, isn't it? What is the total area of the sphere? So we say kq over r squared times the area of a sphere. What is that? 4 pi r squared. And you see what happens to r? So the phi flux of electric field due to this charge at the center is equal to 4 pi k cubed, right? R squared goes away. We have another name for 4 pi k. So the flux of electric field due to this electric point charge is the charge divided by epsilon naught. Remember, that is for just a point charge at the center of the sphere, right? What if you have another sphere that is a different radius around this point charge, with this centered at this point charge? Would the flux be different? No, because the radius cancels out, right? So flux of this electric field of this electric charge around any surface, any sphere, that this charge is at the center is the same. And another way to look at this is that if you make a small cone with the tip of the cone at this charge and make a very narrow cone like this, the flux going through this and flux going through this is the same. So this is a small cone with a very small solid angle. And if you make that cone of rays, flux going through these two are the same. And you see why. The further you get, the area increases by square of the distance, but the electric field decreases by square of the distance. So these two cancel the effect of each other, right? That's why the flux through any sphere with any radius is the same. It's always Q over epsilon naught. But what if we have the charge not at the center or is off center? What do you think? Or if you have a charge inside a closed surface but is not a sphere. This surface is not a sphere. Let's say it's any random surface and you have an electric charge in here. What is the flux through this surface from this charge Q? I can put a sphere around that point. And if you put a sphere around this, so that the charge is at the center, now if you make the same cone in here, let's say, can I say that the flux going through this piece is the same as flux going through this piece? Because you see this is further away, the area is increased by distance squared, and the electric field also decreased by square of the distance. These two cancel effect of each other. If you do it here, this is at an angle. When this surface is at an angle, it may be a bit different. But remember, like what we did over there, if it is an angle, at an angle, the area is bigger, right? And you multiply it by cosine theta. So the area becomes bigger by cosine theta, but there's an angle between the area vector and the electric field vector. This cosine also cancel each other. So the flux going through this surface is the same as flux going through this surface. And if you move this around everywhere, you see that every contribution to the flux of going through the sphere is the same as some contribution from the other surface. So the flux going through the other surface is also the same. So even though this was for a sphere, now you can see that this flux of the electric field of a point charge going through any surface that's around that point charge is Q over epsilon naught. So this is more general than just being for a sphere at the center. What if Q is outside the closed surface? What do you think? If you have a closed surface and you have a charge Q outside of it, what do you think the net flux through this surface is? Again, make a small cone. The flux going through this and this have the same magnitude, but one is, you see the electric field here is this way, E, and dA is this way. E and dA are in more than a 90-degree angle. And this flux is negative, right? And this side, the electric field is this way, and the dA is that way. And this here is positive. and have the same magnitude, right? As we said, for this ray. So the electric flux here is negative, here is positive, and the same magnitude. If you move this over the whole surface, you get some negative, some positive, and they cancel each other. So if it's outside, then flux of E is equal to 0. In general, if we have a charged particle of charge Q making E field E and the surface, then the integral of that E field, that dA, over the surface is phi E over that surface equal to Q over epsilon naught if Q is inside the closed surface. And phi E is, which is integral E dot dA, is equal to 0 if Q is outside. Right? So this is a general statement. Now, what if we have a collection of charges? I'm just building up step by step what is Gauss law. I can give you the Gauss law, but then it is hard to understand the generality of that law. Suppose we have a collection of charges. For collection of charges, Qi, I from 1 to n. Means Q1, Q2, Q3 up to n. Total electric field created by these charges is, remember, said electric field has superposition property. So we add all these electric fields due to each one, I from 1 to n. It gives you the total electric field, right? And then, if you have a surface, phi of total E on that surface will be integral over the surface of E dot dA. And this E is sum of all these EIs. So you can write it as integral of summation of EI dot dA, right? But because dot product is distributive, I can write this as integral of sum of EI dot dA and because integral is a linear operator, we can sum of all the integrals, right? I can take summation out. Sum of integrals of EI dot dA. And what is this? For each one, it's like that. Depends on whether the charge, ith charge, is inside that surface or outside. If it is inside, there's a contribution here. If it is outside, the contribution is 0. If it is inside, the contribution is Qi over epsilon naught, right? So the total flux will be sum of all the charges that are inside divided by epsilon naught, isn't it? Because for each one of these, if the charge is inside, there's Q over epsilon naught for that. If the charge is outside, is 0. So this becomes all the charges, that's integral of E dot dA becomes sum of the charges inside, so let me call it Q in over epsilon naught. And this E is created by all the charges, whether they are inside or outside. That's very, very important. This E is not just created by these charges that are inside. This E is created by all the charges in the universe. But the amount of the integral over that surface only depends on the charges that are inside that surface. And that is the Gauss law with all its generality. It's very, very powerful. It says no matter what creates the electric field, integral of E dot dA over any closed surface is equal to sum of all the charges inside divided by epsilon naught. And of course, remember that if the charge is positive, integral E dot dA for that charge is positive with positive charge Q. If the charge is negative, negative charge. So these charges add up like scalars. If you have the same amount of positive charge and negative charge, they cancel out each other. If you have extra positive charge, the net E dot dA integral is positive. If you have net negative charge inside the surface, the flux through that surface is negative. So this is completely general. And the electric field is not only created by these charges, it's created by all the charges, which is very important, and only depends, this integral depends on how much charge is inside. And that's Gauss law. All right. So in here, actually, we saw that how from Coulomb's law, we get to Gauss law. The other way around is also possible. Means if you consider only the Gauss law, you can conclude Coulomb's law. Means that these two laws, Coulomb's law and Gauss law, are exactly equivalent of each other. There are two ways of saying the same law. But this Gauss law has some properties that are sometimes more useful. If the problem has some symmetry, it's very useful. For example, if you have a charged conductor, now you have a conductor, you have some extra charges on it. Either you remove some electrons, it becomes positively charged, or add some electrons to it, you get negatively charged. Where is the charge on the conductor? That is something that is hard to understand from Coulomb's law. But from Gauss law, it's very easy to understand. We have a surface, we have a conductor, and it has some charge Q on it. Let's say it's positively charged. We want to see where the charges are. Any idea? What is your guess? What is a conductor? Inside the conductor, the electric field should be zero, because if the electric field is not zero, the electrons will move, because they can easily move until they rearrange themselves to make the electric field zero. As long as the electric field is not zero, the electrons will move. So a conductor in equilibrium has zero electric field inside of it. Does that make sense? E field inside a conductor is zero everywhere. This is our conductor. So, because it is a conductor, the electric field should be zero inside, right? So what does the Gauss law tell us about this? Let's imagine a surface, closed surface inside that conductor, so that all this part of this surface is in the conductor. What does the Gauss law say about this? If the electric field everywhere is zero, means that what is this integral? Integral is zero. E0 dot dA at any point and integrate over the surface, you get zero. What does that tell you about the charge inside? Zero. Means that as long as you have all the part of the surface inside the conductor, Gauss law tells you that there is no net charge inside that surface. Does it make sense? Because the electric field is zero, integral is zero, therefore Q inside is zero. Now let this surface increase and increase, but remain inside the conductor. So let it approach the surface. As long as it is inside the conductor, the total charge inside is zero. Means that any extra charge that you have on a conductor is only on its surface. No matter how much charge you have, none of it goes inside the surface. No matter what shape it has, no matter how much charge you have, it's all on the surface. That is something that you get from Gauss law. It is hard to get it from Coulomb's law. Of course, from Coulomb's law, you can say they repel each other, so they go to the surface. But on the surface, they should repel each other, so some of it may be forced inside, right? But Gauss law says that no, all of it is on the surface, no matter how much charge you have. So all extra charges on a conductor are on its surface, on its outer surface. Even if you have a cavity in here, and there's no charge inside the cavity, no charge in the volume inside, there's no charge on the surface here either. All the charge goes on outer surface. If you have a charge inside the cavity, what happens is that you have a conductor, there's a cavity inside the conductor, and you have a charge Q in here. It's suspended there, it's not in touch with the conductor. There's a cavity, there's a charge there. What do you think? Again, do the same thing. You consider a surface here. The surface that we consider and we apply Gauss law to it, we call it Gaussian surface. Let's say this is a Gaussian surface. This is surface of the cavity, this is the outer surface of the conductor. The conductor is all in here. There's no conductor inside the cavity. There's the inner surface of the conductor, surface of the cavity, and there's outer surface. If you consider this Gaussian surface, what is the electric field over this Gaussian surface? Because it is all inside the conductor, the electric field is 0. The integral of that equals 0. Means that the net charge inside that surface should be 0. Means that if Q is here, then negative Q should be somewhere else, right? And then you make that Gaussian surface approach to that surface of the cavity, keeping it inside the conductor, tells you that if there's Q charge here, negative Q is right at the surface of the cavity. So if you have a charge inside the cavity, it attracts the same amount of charge opposite to itself on the surface of the cavity. Nowhere else, just on the surface of the cavity. If there's no charge inside the cavity, then there's no charge on the surface of the cavity either, as we said here, right? So this is one of the conclusions of the Gauss law.